Hello friends, in this particular lecture we will look at the health-based ventilation framework. So we have looked at infiltration, we have looked at ventilation and some derivations on the air exchange rate, how the overall ventilation has to be designed. We will look at the framework on how it has been or it is generally designed, and also we will look at some special cases of pollutants and specifically of course through the infiltration or outdoor to indoor pathway sense. So historically the purpose of ventilation was considered to just to provide sufficient fresh air from outdoors. It was in historical context, of course the industrialization or maybe the pollution maybe was lower earlier times, and it was always thought that the outdoor air is cleaner and providing more flow of outdoor air to indoor air will help us sort of freshen up the indoor environment. And generally it was considered that the indoor air impurities will be removed, impurities such as CO2, moisture, and of course whatever the other emissions are happening inside, so cooking or cleaning or dusting. So bringing air from outside will then sort of flush out the indoor air, and the indoor air will freshen up. Of course, in the recent times when the outdoor air itself is polluted, ventilation is also considered in the context of infiltration of outdoor pollutants, because now if the house has a window and it's just next to a very busy road, there is a lot of emissions outside, and in this case having more ventilation is probably worse for the indoor air quality. So in more modern times, we have to consider these kind of situations also. What is the outside source? How is outdoor air? Is it like traffic area, or is this an industrial area? And we have to consider this ventilation also in the context of the outdoor pollutants. In general, our healthy indoor can now only be possible by considering pollution from outdoor also, pollution from outdoor air, and what is generated indoor also. So we have to look what was considered historically, that indoor emissions were there and outdoor was freshening up, but of course now outdoor is not necessarily freshening up, outdoor itself can be polluting. So we have to consider both, that the pollution can come from outside and also of course pollution can come from inside. So healthy indoor can be possible only by considering pollution from outdoor air and that generated from indoor environment. So now the effect or the use of ventilation becomes multi-pronged. Reduce exposure to hazardous pollutants in the indoor environment. So somehow we have to devise our ventilation scheme that can in the end reduce the pollution exposure indoors. Therefore, it can reduce the associated health risk. And when we have less emission, less hazardous pollutants in the indoor air, our health risk is also likely to decrease. And then when the health risk is decreased, we have an increase in the overall comfort and well-being of the inhabitants. So now our ventilation goal is to reduce the final hazardous pollutant exposure indoors, regardless of where the pollution is coming from, and this will be then expected to lead to health benefits and the overall comfort. So what is the principles for the framework for health based ventilation guidelines? So the resulting design concentration must be less than the permissible limits by the applicable authorities. So what we will know is this much concentration is allowed so that the risk to health do not become appreciable. So we have to provide ventilation in such a way that our design concentrations must be less than the maximum allowable limits. Of course, we are thinking of ventilation as an amelioration, as a mitigation factor. The most important thing actually remains the source control, because if the source becomes cleaner, then the ventilation, of course, the requirements of ventilation must be relaxed. So source control is very important before even thinking about the ventilation. Having said that, some base ventilation has to be maintained. This is to remove whatever the indoor pollution is generated by the inhabitants. For example, we may be removing or emitting microbes through our breathing or through shedding from the skin. So some basic ventilation must be there to remove this kind of microbial contamination or microbial load, and maybe also some base emissions of other chemicals as well possible. So we have to maintain some base ventilation all the time. How will the framework work? So now we have first in our framework the consideration for outdoor air, and we have certain ambient air quality. So concentrations of whatever chemical or particulate matter in the outdoor air. This is generally governed by where the building is located. Is the building located near traffic sources? Is the building located in a very clean forest, near forest, in a very clean environment? Is it near, is it inside a very residential or a urban residential setting, or is it more in a very rural setting? Is there construction activity going on? So that, where is the general location of the building? Where is the location of the air intake? Is the air intake close to the location of the outdoor source? If there is a highway, is my window opening to the highway, or is my window opening to the other side of the highway, which may possibly have less pollutants? Is my window next to a construction building, or is my window towards the indoor of the inside of the apartment complex, where there is comparatively less pollution or particulate matter load? Then what is the air tightness? So we have the building location, we have the air intake location. What is the general air tightness? What is the sort of leakiness factor or leakiness propensity of the building? Because you can control the ventilation, but how will we control the leakages through cracks or any other situations? So when we have ambient air, the next consideration is the ambient air itself according to WHO guidelines for such air? If no, then we have to go for some air cleaning. So the ventilation system itself must have some cleaning mechanisms. Could be installation of filters, for example, or any other mechanisms. But if the outdoor air itself is in of poorer quality, not meeting the World Health Organization guidelines, we must actually clean the air first before letting it inside. So if the ambient air itself does not qualify this ambient air WHO guideline, we must go for air cleaning, which could be the design and maintenance of the ventilation systems. And then we will go back to our flow chart and check if the ambient air quality guidelines are met as per WHO. Assuming they are met, then we will look at the indoors. So the ambient air after cleaning, after ventilation, filtration are met, and then we look at indoor. So now we are looking at our indoor air, and indoor air will have some indoor sources. So these could be building materials themselves, or these could be the use of certain products. So building materials could be, flame retardants on the wall, maybe furnishings are there. What type of product use is happening? Are we doing some cleaning activity through mechanical vacuum cleaner or some grinding? What are the other activities? Are the people smoking or walking around a lot, which will lead to resuspension of dust? So mm, our clean air is coming in, and we are now in the clean air is coming in inside the room, and in this room we have some indoor sources. So now we have some build up, some certain quality of indoor air. Now we are coming to here, indoor air. So that was our outdoor ambient air quality guidelines. If they are satisfying, good. If they are not satisfying, we go for air cleaning in the ventilation system, and we come indoor systems, indoor air, where we have indoor sources through these situations, building materials, product use and activities. Now we will check what is the situation now. Is the indoor air quality according to the WHO health guideline? If yes, good. If no, then we have to go for indoor source control. which is we have to somehow ameliorate these sources from here. Do we need to improve our cooking mechanisms, or do we need to use some better building materials? So how, what kind of products we should use? So if we do indoor source control, we control these kind of sources, and then again come back and see what is the indoor air quality possible, and will this satisfy the WHO guideline? If yes, then we go for designing the health-based ventilation rate based on this complete framework system. So this sort of tells us how the framework of the ventilation, health-based ventilation rates will be done. How will we utilize this? In general, environmental burden of disease models have been used. So basically, how much pollution exposure can lead to some premature mortality in a population. And generally, outdoor air quality in indoor sources may be assumed constant. Now, we can optimize the ventilation rate alone. If we do that, for example, to a value of 4 liter per second per person, easily, or the studies have said that up to 20% reduction in the disease burden can be achieved, which is attributable to indoor air pollution. So we would have a certain burden of disease attributed to indoor air pollution, and if we optimize the ventilation rate alone, in this case about to 4 liter per second per person, we can already have a 20% reduction in this disease burden. If we go ventilation rate below 4 liter per second per person, the burden of disease generally increases rapidly. So we must maintain some minimum ventilation rate. If we increase the ventilation rate, the burden of decrease, the reduction of burden of disease will be better, but maybe not so much, because we also have infiltration of fine particles coming in. So we are, we have to optimize our ventilation rates as well. It has been found that filtration of outdoor air leads to substantial improvements in the air quality and the health. For example, a 50% filtration efficiency already led up to 30% decrease in the overall disease burden. Maintaining, if we do maintain optimal ventilation rate 4 liter per second per person and reduce the indoor sources, we can again receive up to 40% decrease in the disease burden. So this optimal use of optimal ventilation rate and the increasing of ventilation rates invariably improves the overall health quality of the people who are inhabiting the indoor environment. Of course, now we can go for filtration of air in mechanic and ventilation system. So we have seen that if we use a optimum ventilation rate and we achieve some filtration, filtration of the out incoming air, filtration will be effective. But this will not be of any use if the building has leakages, for example, through cracks. In fact, it has been reported that even a very high filtration, up to 95% filtration of the incoming air, will be rendered ineffective if the building has leakages. So the leakages are sort of countering the entire effect of our good ventilation, good filtration of incoming mechanical ventilated air. For example, 50% leakage would already lead to an approximately only 50% improvement in quality. Although I was achieving 95% filtration of incoming air, if there was a 50% leakage, we will only get 50% improvement in air quality. So sort of leakages are substantially diminishing the impacts of having a filtration in mechanical ventilated systems. Filters generally also effectively remove the ultrafine and the coarse particles, but the efficiency is lower in the particle range 0.1 to 1.0. We will look at this more in the lectures on indoor aerosols. So this is the size bands where the efficiency of filtration also reduces. So not almost always filtration will be good, because we are having a low efficiency of removal in the 0.1 to 1.0 micrometer range. So that was about filtration and particulate matter. Now we will look at certain special cases. The first case is the case of radon infiltration to indoors. In general, radon exposure causes lung cancer, and 222Rn is the most relevant isotopes. Mostly it is produced from outside the building. Alpha particles from radon, they can reach the lung tissue and cause the cell damage. Now we have radon, which has a substantial health impact, and this is a soil which is naturally rich in radon. Now in the aquifer there may be a fractured bedrock. So somehow through these fractures the radon is infiltrating to the basement, and then again through cracks it's coming inside. Sometimes this radon can be reaching this groundwater borewell, the water in the groundwater borewell, and then through water it comes to our water systems, and then one person takes shower, the person becomes exposed to radon. Radon can also infiltrate through the sumps into the house environment, and also through the windows, or maybe the radon goes up and reaches the outdoor environment of the house, and then through the windows it comes inside. So there is a lot of pathways through which radon can infiltrate inside. The radon world WHO health based guideline is 100 becquerel, which is BQ per meter cube. This becquerel is the activity in which one nucleus decays per second. This guideline is often exceeded in buildings which are in places with geologically rich uranium, and from uranium decay we have radon, and the radon causes the exposure. So radon, as we've seen from the previous figure, it generally reaches buildings via infiltration from soil, but it can also come from outdoor air in buildings with the leaky foundation. So when the building has leaky foundation, the radon comes from soil to the outdoor air, and from outdoor air to indoor air, maybe via windows or doors. And levels have often been reported to reach up to 1000 becquerel per meter cube. Now radon exposure increases risk when there is a co-exposure, for example through tobacco smoking, and the risk increase for a tobacco smoker, the risk increase linearly with increase in radon exposure, up to 10% increase in risk at 100 becquerel per meter cube, which is basically the health based guidelines. So even when the radon level is within the health based guideline, when there is a co-exposure, this a person who is smoking tobacco is exposed to this radon, which is up still within the WHO limit, there is a still 10% increase in the exposure risk. Increase in ventilation, because the radon has so many different sources, infiltration, direct infiltration, or coming from outdoor to indoor. Increase in ventilation can both increase or decrease the exposure. When ventilation is from free and cleaner atmosphere, ventilation will dilute the radon penetration from soil, whereas and then this ventilation will dilute radon penetration from soil and reduce the this is radon exposure. I will just correct this spelling. So ventilation will dilute the radon penetration from soil and reduce the radon exposure because the outside is free. If the ventilation increases the suction of radon from soil or foundations to outdoor air and then outdoor to indoor, ventilation will actually end up increasing the radon exposure. The next special case is second-hand smoke from outdoor air. So in general, it has been found that there is a lot of workplace smoking bans. So when there is smoking ban in the workplace, there is a decrease in the direct indoor source. But now the smokers are going outside to smoke. So when the person is smoking outside, now this outdoor air can also potentially come inside. So the smoke can move back indoors. In fact, the studies have shown that smoke-free indoor areas and outdoor areas have more second-hand tobacco smoke. when they are close to the outdoor smoking zones. So this is because maybe there is a window which is close to the smoking area, and the smoke comes in, and this indoor area has more secondhand tobacco smoke. Also, higher nicotine level indoors have been detected in bars and restaurants which have actually outdoor smoking areas and not indoor smoking areas. So now the outdoor smoke is coming indoors. So when this is the situation, how can we adopt some mitigation measures? This can be done by applying some mitigation measures near buildings. For example, no smoke zones at the entrances, because entrances are open place where people come in. If there is a smoking there, the smoke will come inside. So we have no smoke zones near the entrances. Also, no smoke zones near the AC ducts and other air inlets, because these air inlets are also bringing air inside. So we should have some zone where there is no smoking. For example, no smoking within 3 to 10 meters of the inlet point, or no smoking within 3 to 10 meters of the entrance. So we are sort of ensuring that the area from which the air is being sucked inside is more free from the smoke. In So those was workplaces. When we look at houses and apartments, sometimes people smoke in the balcony. So smoke from balcony can run indoors of a person's own apartment, or even the neighbor's apartment or neighbor's house. In some studies that have been carried out in apartment complexes, it has been found that up to 40 to 50% of non-smoking units have reported experiencing second-hand smoke. Similarly, even nicotine has been detected in majority of units, even if there are non-smokers. And the indoor apartment area is non-smoking, but when people smoke on the balcony, this nicotine and smoke comes inside. And this has been reported in several countries. So in general, this phenomena will be depending on the building and the apartment complex characteristics and design. How likely a person smoking in the balcony is going to influence the neighbors depends on the building or the apartment complex design. So now we can summarize this particular week. We have seen that outdoor air is an important source of indoor air pollution. The ventilation of indoor air can be through natural means, solar chimneys or windows, or mechanical through fans. Coarser particles and gases such as ozones can be filtered out more by the building envelope by various processes. Particles in the PM 2.5 size range, or in the size, especially in the fraction 0.1 to 1 micron, and gases such as NO2 will infiltrate more efficiently compared to the above and are less filtered out. Also, this kind of PM and other gases in outdoor airs are also infiltrated efficiently. Infiltration through cracks and leaks and mechanical ventilation is generally size dependent. Uh, in few cases, the pollution can enter also through soils and basements, especially in the case of radon. Second-hand tobacco smoke can also travel indoors from outdoors, as we have seen, for example, in a building scenario or in an apartment complex, or a workplace. There are a lot of situations in which second-hand smoke can actually come from outdoors to indoors. Higher ventilation rates will lead to higher indoor exposure if the source is outdoors, because then we are bringing pollution inside. Filtration will help. It will reduce indoor pollution, but only if there are no leakages in the building, because as we have seen, leakages tremendously reduce the efficiency of filtration towards reducing the health burden. Energy efficient buildings will generally minimize ill filtration, but since we are minimizing the ill filtration, these buildings can help in the accumulation of indoor pollution such as moisture and microbes. Higher ventilation will generally reduce the indoor exposure if the outdoor air, so to speak, is cleaner than the indoor air. In summary, when we are designing this ventilation or exchange rates, careful considerations will have to be made when calculating the design ventilation rates. So, with this we conclude this week's lecture.